This video will introduce you to torque, which is kind of like the rotational equivalent of force. For starters, I want you to think about what you could do to cause a change in something's rotational motion. Maybe we're starting something rotating when it was initially stopped, or perhaps slowing something down and stopping something that's initially rotating. In either of those examples, to do that, we must apply a force, but not just any force, because sometimes a force that we apply doesn't change something's rotational motion. For example, let's think about a door again. Just any door, a door inside your house perhaps, or a door into a classroom. If I were to press down on the top of that door, it wouldn't cause the door to rotate, even though I'm applying a force. Similarly, if I were to push inward on the door, near the handle, but pushing toward the hinges, that wouldn't cause a change in its rotational motion either. So, applying a force is not enough information to talk about what causes a change in something's rotational motion. Instead, we have a new concept. Rather than applying a force, we will apply a torque. That means we got to define exactly what a torque is and figure out how we can calculate a torque. So torque, which is simply something that has the possibility of causing a change in rotational motion, depends on two quantities. The first quantity is one you might have already guessed. Since we've been talking a lot about force, it must depend on force. But it also depends on where that force is applied. If you think about it, in opening a door, where is the door handle always located? It's always located as far from the hinges of the door or as far from the axis of rotation as possible. If I were to put that door handle in the middle or maybe close to the hinges, close to the axis of rotation, it would be a lot more difficult opening and closing that door. That tells me that torque depends not only on how much force you apply, but also on something we call the radius. It's important to note that the radius in this case refers to how far the force is from the axis of rotation. Not all of our rotating objects will have radii like we're used to with circles. So, if a torque depends on these two things, there's the symbol for torque. It's actually a Greek letter. It's the Greek letter tau. And it's equal to the magnitude of the force times the magnitude of that radius. That's not all. Because if this were the equation, just force times radius, then those examples I gave earlier of pressing down from the top of a door or from pressing inward toward the hinges, those would still cause a torque, which means they'd cause a change in the door's rotational motion. And if you've tried it, they don't. So that must mean that there has to be more to this equation. And the more to this equation is the sine function. The equation for the magnitude of torque is that it is the magnitude of force times the radius times the sine of theta. Just to reiterate, the radius in this case is the distance from the axis of rotation to where the force is applied. And radius in this case is actually also a vector. That vector starts on the axis of rotation and points to where the force is applied. Theta in this equation is the angle between the force vector and the radius vector when those two vectors are placed tip to tail. I can look at my equation to help me figure out the units. We know force is measured in newtons, and radius, being a distance, is typically measured in meters. Newton meters are the unit that we use for torque, although technically, if we were to write this out, we know that a Newton is a kilogram meter per second squared. And when I multiply that by meters, I get kilogram meter squared per second squared, which we defined in an earlier chapter to be a joule. You should never use the unit joules for torque. One last fact about torque, and that's the fact that torque is a vector, which means that it needs a direction. For the sake of honors physics, we'll use either clockwise or counterclockwise for our directions. To determine whether a torque is clockwise or counterclockwise, you'll want to ask yourself the question, what direction would my object rotate if the force that is causing this torque were the only force acting on it? If the force would cause a clockwise rotation, then your torque is clockwise or negative. If your force would cause a counterclockwise rotation, then the torque is positive. Let's see all these concepts about torque, how they play out in an example problem. In this example problem, one end of a meter stick is fixed in place while the other end is free to move. We have a force of 15 newtons that's applied normal to the stick, which causes a torque of magnitude 12.8 newton meters. We're asking to find where this force is applied on the meter stick. Let's start by drawing a diagram. Here's my meter stick, and it says one end is fixed. In other words, that end can't move, which makes it our axis of rotation. It tells me that we have a 15 Newton force applied normal to the stick. We have seen this term in physics before, with the normal force. Normal in physics always means perpendicular to. So our force is perpendicular to the stick, which means it's either pointed upward or downward. We don't know which, and it really doesn't matter here because we're only looking at magnitudes. And we also don't know where that force is located, so I chose a random location here. One other thing that I'll add to my diagram is the radius vector. The radius vector starts on the axis of rotation and points to where that force is applied. So here's my diagram, and now that I have my diagram complete, let's look at the equation. The equation tells me that the magnitude of torque is the magnitude of force times the magnitude of the radius times the sine of the angle between the radius and force vector. If I were to put the radius and force vector tail to tail, I'd see that the angle between them is 90 degrees, and the sine of 90 degrees is 1. That means that if I'm trying to solve for where that force is located, which means I'll find the radius, I simply need to take the magnitude of torque divided by the magnitude of the force, or 12.8 Newton meters divided by 15 newtons. When I plug those numbers into my calculator, I find that this force is located at 0.853 meters from the axis of rotation, or the 85.3 centimeter mark. In class, we'll do some more problems dealing with torque. We'll look at things like calculating the net torque on an object, and we'll find out how we can determine how the torque would actually affect or would actually change something's rotational motion.